Kawasaki has replaced the ZX-750H2 with two new completely redesigned models, the ZX-750J1 and the ZX-750K1. New models improve on concepts introduced on the ZX-750H2. The frame and front forks have been improved to provide greater rigidity with less weight. These changes combine to improve the new model's race-winning potential. The new engine is lighter, more compact, and revs smoothly from idle to redline. The race-winning potential of the ZX-750K1 is further improved with the availability of a racing kit. In this presentation, we will explain the features of the ZX-750J1 as they compare to the ZX-750H2, which we will now refer to as the H2. We will be looking at features of the frame, features of the engine, the difference between the ZX-750J1 and K1 models, and give you some pointers on carburetor adjustment. First, let's look at the features of the frame. The new models have diamond frames which provide superior torsional rigidity. The steering head and swing arm brackets are made of extremely rigid cast aluminum. To reduce weight, the bracket areas are hollow. These cast aluminum parts are connected to the main frame members that are made by welding stamped aluminum plates together. The techniques used in the construction of the frame allow for great flexibility in design. Each part of the frame has only the material required to provide the rigidity necessary to cope with the stresses in that area. This allows the frame to have all the strength and rigidity necessary with the least weight possible. The rear frame section is made of rectangular aluminum tubing and is bolted to the main frame. The steering head stem diameter was increased to 35 millimeters for improved rigidity. Front suspension is by cartridge type male slider forks. When mounted in the triple clamps, the large diameter upper fork tubes combine to produce a front suspension that has superior torsional rigidity. The increased rigidity of the front forks make it possible for the frame and suspension to work together to provide precise, stable handling in corners as well as on a straight line. The forks are cartridge type with adjustable rebound damping. This design provides more consistent performance because the cartridge stays submerged in the damping oil, making it very difficult for air to mix in and reduce the oil's effectiveness. Spring preload can be set using an adjuster on the top of the forks. A 12-position rebound damping adjuster is provided in the center of the preload adjuster. As with the H2, a nitrogen gas-filled rear shock is used, but the spring weight and damping force have been changed. The shock features four-way rebound damping and a threaded preload adjuster. The Unitrack rear suspension has been changed from progressive to the linear proportional type. This change minimizes the bike's tendency to jack up and down under hard acceleration and braking. To maximize rigidity and minimize weight, the swing arm is made using the same technique as the frame. The swing arm pivots on caged needle bearings with an additional ball bearing on the right side to control thrust loads. The swing arm remains centered in the frame to assure smooth operation. The pivot shaft is hollow to keep weight down, while its diameter is increased to 25 millimeters to improve rigidity. The diameter of the semi-floating front brake discs was increased to 320 millimeters to provide much more reserve and braking ability. The greater diameter helps dissipate heat more effectively, improving fade resistance. The front and rear brakes are equipped with opposed piston calipers. The front are 4-piston and the rear 2. The low-profile 120/70 VR17 radial front tire is used. Another change from the H2 is the use of a wider lower-profile 180/55 VR17 rear tire. The lower profile increases sidewall rigidity for improved traction. To help maintain the rigidity of the male slider forks, the diameter of the front axle was increased to 25 millimeters. The front axle is hollow for weight control. The diameter of the rear axle was also increased to 25 millimeters to increase the rigidity of the rear suspension. It also is hollow for light weight. The full floating rear brake has its torque link attached to the frame. The electrical system has been improved with the addition of a maintenance-free battery. This battery is the sealed type, so there is no chance of electrolyte leakage. By shortening the wheelbase 35 millimeters to 1,420 millimeters, the bike's agility has been improved. Now we'll look at the features of the engine. This engine is an entirely new high-performance DOHC 16-valve, water-cooled, inline-4 design. Downdraft CVKD38 carburetors are used. The carburetor intake angle is set at a steep 47.5 degrees. This decreases air induction resistance by providing the air-fuel mixture with a nearly straight path to the combustion chamber. There are no steps in the ducts that connect the air cleaner to the carburetors. This allows a smooth flow of air, which improves air induction efficiency at medium and high speeds. The valve train is driven by a roller chain which turns the camshafts. A roller chain has real advantages over the more commonly used silent chain in a high RPM engine. The weight per length of the roller chain is much less than that of the silent chain, reducing chain swell at the sprockets caused by centrifugal force. The right-hand outermost camshaft journals are supported by ball bearings, which decrease friction loss and increase durability. Valve timing is set rather mild to produce maximum torque at low engine speeds. Duration is 260 degrees for both intake and exhaust valves. Small, lightweight rocker arms are used to enhance their ability to follow the cam loads at high RPM. For the first time in the 750 class, a single spring is used on each valve, reducing reciprocating mass and mechanical loss. The springs are made of high-purity steel for improved durability at high RPM. To increase intake and exhaust efficiency, the diameter of the valve heads was increased, the intake to 29 millimeters, the exhaust to 25 millimeters. To compensate for the additional weight of the larger valve heads, the diameter of the valve stems was decreased to 4.5 millimeters, further improving intake and exhaust efficiency. The diameter of the camshaft sprockets was reduced, allowing a very shallow included angle of 20 degrees between intake and exhaust valves. This narrow angle makes a compact combustion chamber possible, resulting in high combustion efficiency. To accommodate the larger valve heads, the diameter of the cylinder bores was increased to 71 millimeters, while the stroke was decreased to 47.3 millimeters. An open-deck cylinder is used to cool the top of the cylinder better where heat is concentrated. Short cylinder skirts are used. This allows the turbulent air in the crankcase to flow smoothly, decreasing pumping loss. High RPM piston ring flutter is minimized by the use of 0.8 of a millimeter thick rings in the top and second grooves. Piston ring flutter is further minimized by the use of a beveled inner edge on the top ring. Combustion pressure acting on this bevel increases the ring's sealing ability at high RPM. Reciprocating mass is further reduced by the use of a 1.5 millimeter thick oil ring. The connecting rods are made of carburized and hardened chromium molybdenum steel. Because of the new short stroke, the rods are only 100 millimeters long, resulting in another reduction in weight. The connecting rod big end is bolted using the plastic region fastening method as introduced on the ZX-750H2. This method precisely achieves the needed clamping force without exceeding it unnecessarily, allowing the use of thinner, lighter bolts, further decreasing connecting rod weight. The crankshaft has 5 main bearings with a camshaft chain driven off the right side. The span between number 2 and number 3 journals was shortened by 35 millimeters. This allowed the crankshaft size to be reduced while maintaining the original strength. The diameter of the crank journals was decreased to 32 millimeters and the crank pins to 34 millimeters with the additional benefit of reducing friction loss. The crankshaft was shortened by 22.6 millimeters, making the engine more compact and lighter in weight. The alternator is mounted on the left rear portion of the cylinder block and is driven by a silent chain. Although the alternator is smaller and lighter, it has increased generating capacity. An additional steel plate and friction plate have been added to the clutch. The steel plate's increased volume provides more heat capacity, improving the clutch's fade resistance. The extra friction plate improves the clutch's engagement capacity by increasing friction area. There is a self-contained torque limiter built into the clutch. Moving to the lubrication system, we see that the rear part of the lower crankcase is a completely separate oil reservoir. Oil, cooled by the oil cooler, flows here first. This oil supplies the isolated area where the oil pickup is located. The oil pickup is so deeply submerged that the oil supply is not reduced or suspended by the oil level changes that occur when the motorcycle quickly accelerates or decelerates. The diameter of the clutch housing gear has been decreased to help reduce oil drag resistance. There are 2 oil pumps in the lubrication system. Splitting the system prevents a drop in oil pressure and lubrication reliability is assured. The oil from one pump is passed through the oil filter, and then some goes to the crankshaft, some up to the cylinder head, and some to the transmission. The oil supply to the cylinder head travels through the rocker shafts to the rocker arms and camshaft journals. Streams of oil from holes in the upper portion of the rocker arms lubricate the cams. Having lubricated the cylinder head area, the oil passes through slots in the raised cylinder head bolt bases and flows down the bolt holes back to the oil pan. An oil pipe located in the upper crankcase lubricates the shift forks by squirting oil out 4 small holes in the pipe. The second oil pump supplies the liquid-cooled oil cooler. Oil from this cooler travels back to the oil reservoir in the rear of the lower crankcase. The oil cooler is installed in the crankcase. This eliminates the need for oil lines, preventing a drop in oil pressure. Additionally, the oil cooler and oil filter are installed in parallel, providing more space for the servicing of these parts. In the oil cooler, hot oil passes its heat to the engine's coolant. A spin-on cartridge type oil filter is used, making filter changes quick and easy. The cooling system has a curved radiator which provides superior cooling. To reduce engine weight, the following covers are made of magnesium alloy: the cylinder head cover, the pickup coil cover, and the engine sprocket cover. Next, let's look at how the ZX-750K1 differs from the ZX-750J1. The ZX-750K1 is a limited production model. It is designed exclusively for solo riding. Also, the K1 has more horsepower in stock form for race-ready performance. Some of the extra power comes from its FVKD39 carburetors. These carbs have 2 mechanical accelerator pumps and a solenoid valve-controlled fuel enricher. The throttle valves are opened and closed directly by the throttle cables. These carburetors provide more precise control of the throttle valve for quick throttle response. Unlike the CV-type carburetor, there is no butterfly valve, improving volumetric efficiency at high engine speeds. These carburetors are at the leading edge of racing technology. The diaphragm-type accelerator pumps supply a richer fuel-air mixture to the engine during the momentary lean condition caused by suddenly opening the throttle valves. This improves throttle response. The fuel enricher provides a richer mixture to the engine to improve throttle response at lower engine speeds. The igniter actuates the solenoid valve located in the fuel line to supply pressurized fuel via fuel pump and nozzle to enrich the fuel-air mixture. The solenoid valve operates under these conditions. The engine is turning within the range of 1,500 to 5,000 RPM, and the throttle is open more than 3/8. The ZX-750K1 has different cam timing from the J1. The duration is up from 260 degrees to 288 degrees on the intake side and to 280 degrees on the exhaust. Inner valve springs are added to the K1 to allow it to rev reliably much higher than the J1. Flat crown pistons increase the K1's compression ratio from 10.8 to 11.5 to 1 for superior combustion efficiency. The ZX-750K1 has paper-based friction plate material in place of the cork-based material in the J1 clutch to hold up rougher use. The ZX-750K1 has a closer ratio transmission than the J1. The K1's aluminum fuel tank cuts weight by 2 kilograms. 7-way compression damping adjustment upgrades the K1 front forks. Compared to the ZX-750J1, the fork tubes are smaller at 41 millimeters in outer diameter and have thicker walls at 2.3 millimeters. The rear shock features 20-way compression damping adjustment, working in conjunction with a 7-way adjustable compression damping fork to suit a wide variety of roads and loads. The rear shock absorber is equipped with a reservoir. Unlike the emulsion-type shock absorber, the nitrogen gas is separated from the hydraulic fluid by a bladder in the reservoir to prevent the air and fluid from mixing. The remote reservoir carries more fluid and is better cooled, resulting in a more fade-resistant shock absorber. The ZX-750K1 has a lightweight fiber-reinforced plastic side cover for one rider and no passenger foot pegs. The rear part of the frame is lighter in weight on the K1 because it doesn't have to carry a passenger. The smaller 8 amp-hour maintenance-free battery also cuts weight. The K1's tires are lightweight, high-performance types. Carburetor synchronization is different on the ZX-750K1 from that of ordinary CV-type carburetors. Also, there are some operational cautions which we'll cover briefly. Before synchronizing the carburetors, warm the engine up thoroughly. Check the idle speed and adjust it as necessary. To gain working room, remove the fuel tank. Rig a remote fuel tank. Attach a vacuum gauge and tachometer special tool to the carburetor fittings. Now start the engine and let it idle to measure intake vacuum. The right-hand end carburetor is the intake vacuum standard. If the vacuum measurements of the other three carburetors are within 2 centimeters of mercury of the right end carb, the system is okay. If the difference is greater than this, adjust the carburetors. Remove the carburetor caps. Turn the adjusting screws to synchronize the other three carburetors to the vacuum standard of the right end carburetor. Do not turn the adjusting screw of the right end carburetor. Turn the adjusting screws clockwise to increase the vacuum and counterclockwise to decrease it. Last but not least, here are some important cautions to keep in mind. Do not operate the throttle on the ZX-750K1 when the engine is not running. The accelerator pumps will flood the engine. Even while the engine is running, do not repeatedly operate the throttle at an idle. The accelerator pumps may foul the plugs with excess fuel. This completes our introduction to the ZX-750J1 and ZX-750K1. For more detailed information on these models, please refer to the service manual.